So today we're gonna dive into chapter 8. But before we actually doing chapter 8, I still want to review a few things because I think chapter 7 is even though that was taught before, but there's a lot of stuff that are very difficult to remember and very difficult to learn. But guys, you need to be quiet unless you want to teach, and I can listen. Um, so I want to review those because without a solid foundation on those knowledge, and you will really have trouble moving forward with this class. And I know one thing that I noticed that many of you did pretty well in quiz number 1. A lot of you did very well, but it was a test of water. It's not really a quiz. I was just kind of give you a sense of what we will be doing. But the quiz will getting more difficult. Um, uh, Even though I said the idea is not to punish you, but to reward you for doing the homework and reading the textbook and listen to the lectures, but still, it's not probably right to get everybody an A in the class. Well, I would take it back. I mean, if everybody's doing well, you all get an A, I don't mind. But still, I want to be fair that it has some level of difficulty so that the people who really study hard would get an A, and then the others would get a good grade. But if you don't spend that much effort, you'll be a little bit, behind. So that's really the purpose. So if you want to, so today we're gonna have a quiz, and then Wednesday we're gonna have another quiz. Just to remind that next week the lectures will be recorded, so you don't have to come here next week. But this Wednesday we still have a quiz. You'll be here, but next week the lectures will be posted ahead of time. So I email you the link, so you'll have a chance to listen to the recorded lecture. And we're gonna have a quiz after that. So on the 19th, February 19th, we're gonna have our our next quiz. And for this week, if you guys want to see me, even you come early than my office hours, feel free to do that. I'm like all day in the office, so you really don't have to wait until the office hour to come to see me. So it's okay to come to me early. But next week, I will try to set some time for online office hours. The best way you want to get in touch with me is to email me so that we can set up a time that we can meet for next week. But the following week, of course, will come back to normal. So let me dive into a few things I want to just to make sure that we all on the same page. So some of the students ask me that, yeah, we are going to use a lot of T-model, but you didn't explain how we get from T-model to from pi model to T-model. So pi model is a simplest one that you can get, but sometimes it makes it difficult to solve for amplifiers, especially when you get into the common source, common emitter amplifiers, or common gate, common base amplifiers. The pi model, you can still solve it, but it's just a little bit more difficult. So therefore, we convert pi model into T model. So for MOSFET, if we remember the T model, if we remember the pi model, so I'm going to also here include the RO. This is D. Again, we're looking at MOSFET as an example. So from here, what we can do is, because the current source in the same branch, there's no current. Remember, there's no current at the gate. So there's no current flowing into the source from gate. So therefore, we can do the circuit like this. So this is still D. And by doing this, what we're going to do is we're going to have You see, the current source is a current source. So they're in the same branch. So you add another current source, you add another current source, as long as the current is the same, they don't change the characteristics of the circuit. So now you see this is the gate, and here is the gate. Because there's no current flowing from gate to source, so what we're going to do, we're going to simply, so let me draw it over here. So we're going to simply connect gate. Let me make sure I did this correct. I made a mistake here. So there's no line here. Actually, there is a line. Sorry, there is a line. So what we're going to do is we're going to connect because there's no, the reason we can connect the G all the way to there is because there's no current. See, from here to here, there's no current. So now I'm simply going to connect it. So once I connect it, this circuit becomes interesting because this is VGS. This is VGS. And the voltage here is GM times VGS. And here is GM times VGS. So GM times VGS is the current. But the voltage across current source is VGS. We can therefore convert this one into a resistance because we know the voltage, we know the current. So the resistance of that circuit can be easily calculated. It's going to be R, we call it RS. It's going to be voltage VGS divided by GM times VGS. This should be same VGS, which is equal to 1 over GM. So this is exactly well how we find the equivalent circuit. So now we have, I'm going to redraw the circuit over here. Oh, made a mistake. So this line is actually no longer going to be that line. And this is the same GM times VGS. And this is your S. So now this is called T model. We basically converted from pi model all the way to T model. If you don't have this RO, and this circuit only becomes this two in series. If this RO, there's something connected over here. So this RO mode is early, the channel effect, you know, the channel effect of the MOSFET, something called early voltage, which corresponding to this one. So that's how you can, from this model to pi model to T model. For BJTs, the pi model again, if we connect RO over here, this R pi, VBE. So what we notice that VBE is a voltage between B and E, right? So if we actually move the capacitor, move the resistor all the way to the gate of E, so this is really E. So what happens if I do this? So this is exactly what they did in the book, right? So if you do this, you will find that this RE this is important. This is different here. So this is IC, this is IE. And you notice that IE equal to IB plus IC. Right? So IE, and then VBE now instead, in this way, VB is R pi times IB. So this is IB. So this is VBE equal to IB times R pi. But in this next one, IE is this, but in this case, your VBE becomes IE times IB. In transistors, BJTs, we know that IE is equal to 1 plus beta times IB, right? So this VBE, we know it. And then we know that this is, sorry, no, that's a mistake here again, sorry. IE times VB equal to IE times RE. And RE is 1 plus beta times IB times RE. And from here, we can get, from here, this circuit, we can get IB equal to VB over R pi. So we can plug in this one here. So we got RE equal to VBE over 1 plus beta times IB. And okay, so here, in fact, we're plugging over here, we get IB times R pi divided by 1 plus beta times IB. So IB cancel, we get R pi over 1 plus beta. So this is your T model. Well, the T model, because it's like got a different tense, so in the future, you simply make this like a straight line. And this RE. This is GM times VB, and this VB, and this IB. So the thing that you need to remember is that this GM times VB is still there at the current. And this RE is much smaller than R pi. Why? Because beta is 100. So if R pi is, say, 1K, your RE would be only 10 ohms. So RE is a very small number. So often, so in the future, sometimes we'll simply neglect it when we do the calculation because it's so small. But of course, in the equivalent circuit, you cannot neglect it because otherwise you will get really no output in this case. Right? So that's how to get from pi model to T model. And then the next one is I want to review, I think we didn't quite get this a lot from last lecture, is on the emitter follower. The emitter follower on this one, we have the output at the emitter, and we have input at the base. We have capacitors. So for the DC circuit, the input and output will be all gone. So the input will be very simply just something like this, and this your VE. So for this circuit over here, we can easily calculate the current of IB and so on. So if we assume this is IB, and this is IE, this RE, this RB. And in this case, we know the 0.7 volts from base to emitter because they're in active mode. But the current over here and over here is different. So therefore, we cannot directly calculate either IB or IE. So we will have to write a loop equation. The loop equation is like this. So we have like IB times RB plus 0.7, then plus IE times RE. And this is equal to VSS or minus VEE, which is, let's call it VEE. So this is equal to, 15 volts, whatever that is going to be. Because IE is beta plus 1 times IB, you plug in this to the equation over there, you can find IB, and then you can find IE, you can find IC. And once you find IC, you can find, for example, GM. Do you remember GM? What is GM? This is IC over VT is VT thermal voltage, and IC is the biasing current. So that's the DC. But for AC, that circuit is a little bit too complex. There's detailed calculation in the book, and also I have some slides later on too. But to demonstrate why is it called emitter follower, let's use a much simpler circuit. Well, this circuit has simply an input. There's no resistance at the gate, simply a AC input. And there's RE here only. There's no output resistance, and the drain is connected to ground. Well, it's can VCC, but for small signal, it's ground. So in this case, we can use either pi model or T model. It doesn't matter because it's fairly simple. So let's start with a pi model. So this is going to be R pi. The collector is grounded, and the current is that, and the output is here. So if we look at the voltage here, the voltage here will be the current, this current times this resistance RE. But this current here is this current plus this current, right? So we can write VO equal to IB plus IC times RE. And IC in this case equal to, I should have not called VGS. It should be called VBE just for consistency. VBE. And IB equal to IC over beta, right? So in other words, you can also say that VO equal to 1 plus beta or 1 plus beta times IB times RE. Okay, so now that's it. So at this point, we need to calculate what the VBE is. If you look at the VBE is here. Remember, VBE is not from there to ground. So VBE is only part of this. So VBE can be calculated as the VBE is calculated as IB times R pi. IB times R pi. So once you got all this, plugging this to here, and then all this one, and then plugging this one here, and plugging this one here, and you will be able to get VO. We can calculate VO. So let's see how much VO is going to be. So VO is going to be 1 plus beta, and beta is IC or IB. So this is going to be 1 plus beta over beta times IC times RE. And IC is, so IC is given at GM times VBE and times RE. And VBE is given here. So, and VBE is R pi. So this is going to be 1 plus pi over pi times GM times IB times R pi times RE. So it's really gets like a little bit tricky because it gets a little bit more like difficult to find the gain. I mean, to find the actual gain between input and output. So because now we got IB, so we have to get back to IB. So we're kind of running circles. So instead, let me run this in using this T model. The T model, the whole circuit becomes with the T model. Hold on. For the T model, we have then we will have the current over here. Remember, this is RE. And we're going to neglect the RO. So this whole thing over here is the T model. This is the ground, and this is our input, VBE, and this is our output. This is the ground. This is the ground. So this is output VO. So for this circuit, if you look at it, it's fairly simple because VBE is connected over here, and the current over there is kind of like given. So that current multiply this one, gives you the whole voltage drop over here, and this is the VO. So VO is equal to that current. So now we can calculate. Let me make sure this RE is correct because this RE is supposed to be the this is the equivalent circuit we call RE. So VO equal to this current here, this current times RE. And this current sometimes can also be written as GM times VBE. Okay. So VBE is from here to here. So you can calculate if we assume better infinity, there will be no current over here. There will be no current here. So you can get VBE right away is here. So we will get VBE equal to I times RE. I times RE. And okay, so we need to get current I. Let me get sure. Okay, yeah. So when we when we put the input over here, so we can see that V input is going to be I times RE plus RE. So this graph. So I think that's where I was having a difficulty. If we put the input here, connect to the gate. So this is input voltage. You see what this input is? This input is the current times this one and times this one. There's two resistance. So input resistance. So now I can calculate the gain is going to be VO over V in, which is going to be RE over RE plus RE. But in this case, RE is much less than RE. So therefore, A equal to AV. Almost like approximately 1. So here I assume beta is infinity. If you don't assume beta is infinity, you will still get a very close, like relation because that current over there is so small. The current over here is kind of very small over here. So mostly the current will be this way. So it's going to be the same thing. Okay, so that's why it's called emitter follower, because the emitter voltage follows the input at the base. The emitter voltage follows the input at the base. So that's why it's called emitter follower. For source follower, it's actually even more straightforward because for this circuit, you have a equivalent circuit of this. We in again to ground. Let's draw it this way, ground. And here you have this RS, this RS, and this is a GM times VGS, and this is the ground, and this your VO. So here you can see, regardless of this VO is going to be GM times VGS times RS. But the next thing is we just need to find out what's the V in. So VO is from here to here. But V in is, we need to figure out what is the VGS. The VGS is from, VG is there to here. So VGS is from this gate to, so from voltage from here to here. So we just have to figure out this one, and then we will be able to find out, let's see. Oh, never mind. I was using the T model, so I make a mistake. Something apparently. So I was using the T model, so forget about this part. So this is your V in is right over here. So apparently over here, V in is going to be GM times VGS times RS plus RS. So therefore, our output over input, which is equal to AV, is going to be RS over RS plus RS. And RS is much smaller than RS, so therefore AV is equal to almost 1. So that's why this one is called source follower, because the output again is very similar to the input in terms of amplification. And also you need to notice that the output is positive, okay? So if we go back to the original circuit where you have all this like input side and output side, the circuit gets a little bit complex. So the only way we can do this is by doing or simplified way to do, is to do the T model. Because the pi model will really get complex, and you have to write node equations and loop equations in order to solve the problem. So in order to solve this, we draw the T model. So with the T model given, and in particular, if we also consider RO between here, this circuit, even with the T model, this circuit becomes more complex. So if you want to solve the circuit directly, you will have to find out like this node here. And there's a node over here. So the easy way to do, if you look carefully, there's a little bit of simplification you can do. For example, RO is from here to where? To ground, right? Because this is ground over here. So in order to make this a little bit easier to look, what I can do is I can simply remove this one and move this one to here. So this is your RO. So now there's nothing here because this is connected to ground, so this is ground anyway, so I simply flip that over. Now you can see these three resistors are in parallel. So in parallel, I can combine them to become one resistor. So simply, I will remove everything here. I just leave it like one RE prime. So that's what I get. So this whole thing is gone, only RE prime. This is my output. This is my like input is over here, but input is over here, become, there's voltage divider. So to calculate the output over here, we have to solve for two, like at least because there's a node here. So we can solve the node analysis by finding out the node voltage here. Once you find the node voltage, you'll be able to find the current. Once you find the current multiplied by RE, you get your output. So the process is fairly simple. The only thing you have to you do is to write the nodal equation over here. And if we write it, it's like this. We need to define a nodal voltage over here. Let's call it VB. So in this case, your current will be V signal minus VB divided by, well, let's do it in another way. So VB minus V sig over R sig, which is the current. So this way, and we need to find the current this way, plus VB over RB plus the current over here, which is VB over RE plus RE prime. And then this all current coming out equal to the current going in, which is the current, which is alpha times R, which is also GM times VGS. So this little bit tricky is this we have to find out what VB is. And VB is from here to here. So VB equal to VB divided by RE prime plus RE times RE. So this is your VBE. You plus VBE over here. You can see right now, you can get VB from that equation. It's just very complex, but you can still get it. Once you get VB, you can find the current divided by this and this. And once you find the current, you can get your output. Once you get the output, you can find your gain. So this is a little bit difficult, but in the book, it gives you a simpler method. It's by looking at the input resistance and output resistance. And the equations have been derived. I think what I'm probably gonna skip this because we don't have the time. And also find the output resistance and things like that, okay? So some of those stuff we're gonna touch again later on in the class because this is such an important concept. But in chapter 8, we are going to talk about a few things. First of all, we're going to look at what are the basic units we need to build an amplifier. So amplifiers today we use, a lot of them like op amps. They're built off of these little building blocks. This is the building block. I would say there are two important blocks. One is the current source. How do you build a current source? Second is how do you build, how do you, like the basic gain unit. We already learned like common source, common gain, common drain, common whatever amplifiers. But we didn't really look at how can you increase the gain. Like we have already talked about many times about this gain and that gain and so on. And also, I think in the next lecture, I'm going to also talk about the impact of input and output impedance. But today I'm going to leave it because I want to dive into the current source and how to do the current mirror, the current steering circuit. For current source, we can build a current source using two kind of devices. We can use MOSFET. We can also use BJTs. They're both used. So we start with MOSFET. When we build a current source, we use two MOSFETs. They're identical, by the way. They're identical MOSFETs. We connect them back to back. And then we connect the gate of one MOSFET to the drain. So for the MOSFET on the left hand, do you know if it is in saturation or in triode or cutoff? It is in saturation. Why? Because the drain is connected to the gate. So remember, there are two conditions for saturation. Okay? So for saturation, we have two conditions. One condition is that VGS has to be larger than VT. Other conditions are VDS has to be larger than. But in this case, we have VDS equal to VGS, right? So as long as we can maintain VGS larger than VT, this is definitely going to be in saturation. Now, how do you maintain VGS more than VT? Because VGS is same as VDS, right? So we can calculate VDS. In this case, it will be same as VD. So here's VD equal to VDD minus ID times R. So if R is small enough, your VDS is definitely going to be larger than VT. So this has to be larger than VT. So if you want to calculate how much ID I can have from this equation, so you can set I max has to be less than VDD minus VT over R. So example, so if VDD is 1.5, VT is 0.5, and your R is 1K, how much current you can have? Max 1.5 minus 0.5 divided by 1 gives you 1 milliamps. Just to give you an example, max will be 1 milliamp. If it was more than 1 milliamps, this circuit will run into saturation. It's no longer going to be in triode or this will be in cutoff if it's more than 1 milliamp. So the next important thing is that given that the drain and the gate are connected, so VGS is kind of being able to calculate it. So we can really calculate I in the other sense to be 1/2 kWOL times VGS minus VT squared. So if we assume that we make it in a saturation, we can calculate current. In this case, we call it as R reference. So if VGS, if I is given, you can calculate VGS. So VGS is given, you can calculate I. So either way, you can manipulate this equation. But once this I is given on this side, how about the current over here, IO? That's a big question for you. How much is IO? What IO is flowing through the MOSFET, this MOSFET. This IO would have to be exactly the same equation that we use, right? So we just simply use KWOL times VGS minus VT. Now, if we want to add this symbol like a 2 to this equation, we can do that. So basically, if we do this, we add this to 1 and 1 and we 1 and this 1 and this 2, this 2, and this is 2, and this is 2. But if this two MOSFETs are identical, what's going to happen? Which means the K is going to be the same, WOL is going to be the same. VGS Oh, by the way, is VGS the same? Is VGS the same for Q1 and Q2? Yes, because this is VG and they're ground. So VGS, so VGS same. So VGS same. So K is the same, WOL is same, VGS is the same, VT is same. What happens for the current? So the second MOSFET will have identical current as the current in the first MOSFET. So that's what is called a current source. Yes. We didn't lose 1/2. Oh, hey, good catch. Here, yeah. And it's squared too. I was in a hurry, so right now, yeah. So 1/2, yeah. So this is going to be the same current. So this is called current source, and sometimes it's also called current mirror, because the second one mirrors the current on. So sometimes we call it current source, sometimes call it current mirror. But there is also a difference. What happens if W over L is different, but everything else is the same? Like K is the same, VT is the same, which means this MOSFET these MOSFETs are built using the same material, the same technology, but only W is different. Even L is the same, or maybe W is the same, but L is different. So what happens then for the current in the second one? Oops, what happened? Oh, okay. Well, I don't know what happened. But so if the, well, in this case, we do neglect the early effect. So if you write the first equation is I reference equal to 1/2 K WOL 1 times VGS minus VT squared, and we write IO is 1/2 K WOL of 2 times VGS minus VT squared, you can find out that IO over I reference, it's going to be WOL of 2 divided by WOL sub 1. So if the second MOSFET has a wider, let's say, width, yeah, W is bigger, so apparently the second one will have a larger current. So it's a proportional. So the second one will have a proportional to the first one. So sometimes they also call this like a current steering circuit, because it's not a mirror. Right? Mirror means the same, but it's really the first one steers the second one to have more current. So to really understand, like, what do you mean steering? Well, let's look at this example. In this example, this one is the reference circuit. And the reference circuit is the same as we just discussed. So this has a current. How much current is in I2? Well, it depends whether they are identical. If they're identical, I2 will be the same as I reference. But if this is like WL is different, this will be different current. How about the current in Q3? It could be the same, it could be different based on the way the WOL ratio. How about the current I4? Same as what? Same as 3, yeah? Because they're in the same branch, of course. So this I4 becomes like kind of a steering circuit for the next one. So what is the current on I5? Same as I4, or proportional to I4, right? So easily we can write I2 equal to WOL 2 over WOL1 times I1. Now, if they're the same, apparently they're going to be the same. Then I3 equal to WOL 3 WOL1 times I1. And I4 is the same as I3, and I5 equal to WOL of 5 over WOL of 4 times I4. So you can see with one simple like a reference current here, we can build many of this current source. So you might ask at this point, what's the point? I mean, why would you do that? Well, in fact, what we do is in the future, we're going to put an amplifier over here. So if we put an amplifier here, what happens to the whole circuit over here? It's just the current source. It's just the current source. So amplifier with the current source. You see a lot of current source in the past, right? So you might have question, where is the current source? Well, that's the current source. And here it becomes the current source. And here, the whole thing over here becomes the current source. We can put an amplifier over here. And the whole thing will become a current source. So this is where you can see the equivalent circuit. We'll put an amplifier over here, and we'll put an amplifier over here. How would an amplifier look like? Well, you see here, it's going to look like something look like this. And here, it's going to have something look like this. And here we have this voltage source. So for both of the circuit, we can simply replace with the current source. Basically, for this one here, it becomes this could be like, yeah, so this goes to negative voltage. And then for this one here, it becomes so you get really amplify with current source in it, that's amplify with current source in it. So it's fairly simple. Why we do that? We want to build current source with MOSFETs. And just to clarify, yes. Yeah. No, they're not in parallel. No, they're not in parallel. This is the current source. So this becomes the reference. And this becomes the PMOS on the top. So this you flip 180 degree, it's the same thing like this. So they're not in parallel. So this is the current, this is the steering circuit, and this is the current source. Yeah. And then we have just clarify one concept. You might hear sometimes they call it current source, sometimes they call it current sink. So really they're the same thing. The only difference is that current source supply current, and current sink absorbs current. So you can think about it in your future, if you have like a sum of circuit, a current, if you use your like a microcontroller as a current source, which means your current, your microcontroller has to be able to supply current to your load resistance. But if your microcontroller is the current sink, which means current will go in. So if you can connect the resistance at the low, it's not going to work because there's no current coming in. You have to current a low voltage source, and so that a current can flow in into the microcontroller. So that's sink. So sink current means it absorbs current. Source means it supplies current. So that's the difference. And we are going to have talk about this. Let's see. Yeah, we still have time. So we can use also BJT to build current mirror and current source. The only difference is that if beta is not infinity, we have a little bit of trouble. But if beta is infinity, so we can, first of all, maybe to assume beta is infinity. If we assume beta is infinity, what happens here? Which means there's no current here. There's no current over here. Therefore, there's no current over here. So let me write down. So there's 0 amps, 0 amps, and 0 amps. And in this case, the two transistors share the same VBE, right? The VBE, apparently, they both immediately connect together. They're both base connect together. So they share the same VBE. And if Now this can be something else. It's like a reference current. We can build it. If that reference coming in, so the reference current going through Q1, how much is the current going to be in here, Q2? So if you remember how we calculate IC, is it going to be, you guys still remember the equation? Can you read it for me? That's right, but that's not what I wanted here. In terms of VBE, there's little e over there. This VT is a summer voltage, not the threshold voltage. So this is what you calculate IC. If these two transistors are the same, you can see that IS is the same, VT is the same, VB is the same. Therefore, this IO equal to I reference. Very simple. If beta is infinity. But if beta is not infinity, we're going to have a little bit of trouble because the current is no longer 0 at the base. So this will be current over here, IB. There's another IB. So this will be 2 times IB. And IB is IC over beta. Right? So we have I reference equal to IC plus 2 times IB equal to IC plus 2 times beta IC, right? So because IB is IC over beta. So in this case, what will be IO then? You know, what is IO? Because from the previous example, we know IO is kind of IS times e to the VB over VT, which is the same as IC. So if we look at IO as a reference of I reference, so IO over I reference, we can get equal to IO I reference is going to be 1 over 1 plus beta over 2. So that's really the only difference over here. Previously, IO and I reference the same if beta is infinity. But in this case, IO and I reference are not the same. The difference is due to that IB that was joined, okay? So with this one, we have IB, but you see the other, so we calculate here. So IC is equal to IS E times VB over VT. If these two transistors have the same VT and same VB was given, but if they have different S, which means, do you guys know what it means if IS is different for BJTs? For the transistor, you know, what does it mean IS is different? Like the saturation voltage, right? Which means the area is different. Area is bigger, the more current. So BJT, the bigger the BJTs are more IS. So not every BJT will same IS. So therefore, your current is proportional. So IC2 over IC1 is proportional to IS2 over IS1. Is proportional to the area of the junction area of the BJT. Okay. So finally, let's do today. I think we're almost done. So here is another circuit that looking at steering, like BJT to build multiple current source. So here is one BJT, another BJT. So from this BJT, you know the voltage over here, and then you will be able to calculate the voltage over here. For the up one, you can calculate the voltage there, so you can calculate the reference current. So once this current is given, how much is this current? This current is same as this. And this current, are the same as this. So the total current I4 is going to be 3 times this current, not I reference. But if that is infinity, of course, I4 is 3 times I reference, I2 is 1 time reference. And I1 is going to be same as I reference, and I3 is twice I reference. If beta is infinity. If beta is not infinity, you have to divide by 1 plus 2 over beta. So that's really that. And finally, this example, this is in the book, so I'm not going to go through very details, but I want to go to the steps, how to calculate the current. You see, we know this is minus 5 volts. Well, when this is in active mode, how much voltage do we usually have? 0.7, right? So which means this 0.7. So this 0.7 and this 0.7, right? Okay. And then look at the top transistor Q1. You know why they mark it Q1, Q2 like that? Because they want you to start with Q1. It's not starting from that side or this side. So Q1, the up is 5 volts. So R2, not R2. Q1, the base of Q2 is how many volts? 4.3. And here is minus 4.3. So 4.3 minus 4.3 divided by 10, you get the current over here. So now you have this current. Once you have this current, you know the current over here, same. So this current over here is going to be twice. So this 0 minus this one times twice the current, you get the voltage over here. Okay? And for this one, you know the current, and you know the current over there. So you know the current of Q11. Now you can calculate the voltage at Q11, right? Because you know the current. And for this one here, you know this voltage over there, and you know the current over here because this current is the same as this current. So the current minus current times 5K gives the voltage drop. So the voltage at the Q3, the base, the emitter of Q3 is calculated. So similarly, you can calculate this current is the same as this current. So this current is the same, and this current is the same as this current. So you know the current over here. So 5 minus current times this one gives you the voltage across there. So this is given, the solution is in the book, so we're not going to copy it. That's all for today. For next lecture, we're going to study to, let me see. So next lecture, we're going to go deeper into gain circuits. So that's Wednesday. And next Tuesday, we're going to do a little bit of cascode, like how to increase the gain of a basic gain circuit, right? So we have basic gain next week, and then the cascode the following week. And by Thursday next week, we're going to go to chapter 9. We're going to look at the multi-stage and the differential amplifiers. So with that, let's close this. Let's log out here. So we're going to have the quiz. So prepare, have 1